we kind of looked at the language of hypothesis testing, how it's set up. So we are going to have our null and our alternative hypothesis. And when we're doing that, are we ever proving the null is true? No, we're trying to prove that it's false. And if we can't, it doesn't mean that it's true. It just means that we failed to prove it was false. So if we take a look at this, some important things. We're talking about hypothesis testing for the population proportion today. So that is our p hat. Remember that all the stuff that we've seen before. P hat is x over n. It's normal. If it's approximately normal, your mean is just your p. The standard deviation is the square root of p times 1 minus p over n. It has to be a simple random sample. To assume normal, these were the two criteria that I made you check. N times p times 1 minus p greater than or equal to 10. And they have to be independent, so the sample is less than 5% of the total population. So we were doing all those on our last test. We had to check our criteria, mean, standard deviation. So all the stuff that we know about p hat is still true. When we are looking at these, we are basically going to find the probability of something happening, and we're trying to decide if it's significant or not. For statistically significant, it means if our results would be unlikely if the null hypothesis is true. So we'll find the probability of something happening if the null hypothesis is true. If it's small enough, that means it's extremely rare, then most likely the null hypothesis is false. Now, is it guaranteed to be false? No, we know unlikely things can happen, but by our best judgment, if I find that the probability of this happening is 0.5%, that would be extremely unusual, so most likely my null hypothesis was false. So that's what we're going to be looking at, and that would allow me to reject my null. There are different approaches for this. So there is what's called a classical approach, there is a p-value approach, and then we will also talk about our calculator. So I am going to kind of run through all of the different options. When it comes to homework, I think I asked you to do one each way, but then after that I'm kind of leaving it up to you to pick your method. So we have to be able to do them by hand, but it's kind of up to you whether you like the classical approach or the p-value approach. Personally, I prefer p-value because it's a little more concrete. You're basically finding the probability of something happening. With the classical approach, you are looking at how many standard deviations it is from the mean. So we know, like the empirical rule, if it's normal, we should see 68% of our data within 1 standard deviation of the mean. Within 2 standard deviations was, anybody remember? Look at it on your formula sheet. Very beginning, the empirical approach. 95% within 2 standard deviations. Within 3 is 99.7. So anything beyond 3 standard deviations is extremely rare. And so basically if it's more than 3 standard deviations above or below the mean, that would be unlikely, so most likely the null hypothesis would be false. So if I look at this problem, a researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving. So p hat is 534 over 1,000. Does this suggest that more than 50% of people favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is some proportion less than 0.5 and we just happen to survey a majority in favor? In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? What is convincing or statistically significant evidence? So, we got 53.4%. Does that seem like, would that be enough to convince you that it's above 50%? Maybe, maybe not. It would have to be a really good sample to convince me, because that's pretty close. But this is the kind of problem that we're looking at. We had something occur, we got something different than our null hypothesis. Is this enough to convince us that it's different? What would the null hypothesis be in this problem? That our proportion is 0.5. Then the alternative, remember yesterday we called that H sub 1. What are we trying to test? Trying to see if it's majority. So we are testing if it was greater than 0.5. All right, so if I were going to continue this problem using our classical approach, we have to think about the probabilities. So first we need to know if it's normal. So we have to check our criteria. So n times p times 1 minus p has to be greater than or equal to 10. What was my n? Yep, our sample size, which was 1,000. Our p, that's the p from the null hypothesis, was 0.5. 1 minus 0.5. So we're testing, is that greater than or equal to 10? And it is. What's the other one I need to check? And I don't have my total population to confirm this, but would 1,000 be less than 5% of the whole population? Yes. So what's the mean and standard deviation? So the mean for the p hat is our proportion, which is the null hypothesis, the 0.5. Standard deviation for p hat is the square root of our proportion times 1 minus proportion over n. And I get 0.0158. Okay, and so if we kind of think about what the mean and standard deviation means. The mean is the center. If we know it's normal because it met our criteria, so approximately normal. The mean is the center. My standard deviation, what did we just say that was? So to get these numbers, you would have to add and subtract your standard deviation. All right, so if you want to be within one standard deviation, it would have to fall between these. Did ours, what was our proportion, our p hat in the problem? 53.4. Is that between these? 53 would be bigger, right? So we could keep doing this to, add and subtract our standard deviation again. We could also just get our z-score. In general, it kind of depends on the problem, but we typically reject if it's more than 2 standard deviations because we know 95% of the data is within 2 standard deviations, right? That's 5% left over. So 2.5% above or below. But 2.5 is considered unusual because it's less than 5. So if you're more than 2 standard deviations, we would say it's probably not likely. So we could find our z-score to measure that, because remember, z-score is how many standard deviations you are from the mean. So our z-score is our score, so our study found it to be 0.534 minus the mean, 0.5, divided by the standard deviation, 0.0158. And we get 2.15. So if you think about what this means, Here's 2 standard deviations. We're all the way out here. Would that be unusual? Yes. It's less than 2.5% chance of being there. So more than 2 standard deviations we consider unusual. So yes, we reject the null. So the classical approach just strictly looks at the number of standard deviations and it doesn't actually find a probability, which is fine. But a lot of times if we want to be more precise, if I want to know exactly how likely it is, the probability is helpful. So that's kind of why I really like the p-value approach. So that's the next one I want to look at. So with the p-value approach, we are going to find the probability. And then if the probability is small enough, we reject. So it's kind of the same thing, a lot of the same problems, or same work to begin with. You have to get your criteria, your mean, your standard deviation, but we'll just go all the way through finding our probability. The p-value is just the probability of something happening if the null hypothesis is true. So when I say find the p-value, that means find the probability of observing our statistic if the null hypothesis is true. And if it's really small, that means then most likely that null hypothesis is not true. So if we think about our example, we already found our z-score. Okay, we want to then turn around and find the probability of that. So we said this was a z of 2.15 from our last slide. How do we do greater than? 1 minus, so we have to get our table. Normal distribution. So the probability of being greater than this is 1 minus, and then we look up 2.15. Is 0.9842. And if we subtract those, we get 0.0158. Is that unusual? Unusual is anything less than 5%. So if it's less than 5%, we would reject our null hypothesis. All right, do you guys kind of have an understanding of what I'm looking at, classical versus p-value? Classical, we basically just stop and look at standard deviations using the empirical rule. P-value, we go ahead and find the probability. So when we do hypothesis testing, remember we have 3 different options for our hypothesis test. We have left-tailed, right-tailed, two-tailed. You can't do a hypothesis test if you don't have a hypothesis. So you have to first write down the null and alternative hypothesis. If you don't have those, nothing else means anything. So that is always the first step. The p sub 0, that just means the p of the null hypothesis. That's the assumed value, so not what we found in our studies, like our population one that we're comparing to. Then we will, oh, I skipped a step, sorry, didn't scroll down. Step 2, we will have an alpha level. Most of the time, alpha is given in the problem. So that, remember from yesterday, is the probability of type 1 error. And so alpha may vary depending on how serious the type 1 error is. You know, if I'm trying to do a survey to see if you guys want to continue having Pizza Hut pizza on Wednesdays, okay, does it matter? I mean, maybe it matters, but is it really that big of a deal if I draw the wrong conclusion at the end? No. So I'll probably have a fairly high alpha value. I could even go to like 10%. Like, is it really that big of a deal if I make the wrong conclusion? No. But if I am doing a new medication and I'm doing a clinical trial with that medication, do I want a 10% fatality rate from taking my medication? No, that would absolutely be unacceptable. So then I would probably want like maybe even less than 1%. So it just really depends on the situation, what your alpha level is. Most of the time it's going to be similar to like a 5%, you know, our standard unusual rate, but it could vary depending on the problem. So that will be given to you most of the time. Then we'll find our z-score. So our test statistic, so it's just our p-hat, our sample minus the null hypothesis p divided by sigma. I have that written weird, but it's just the z-score. Then, if you are looking at the classical approach, you have to find the z-value that matches your alpha. Okay, we were doing two standard deviations because that was like alpha equals 5%. But if alpha is different, that number of standard deviations would change. So we would have to find the z-alphas, or if you're doing two-tailed, z-alpha over 2. And that's why I kind of dislike the classical approach, because you have to think a lot more what's acceptable and what's not. And then if you're in that shaded region, what would you do? If you're in the shaded region, you would reject your null hypothesis. If you're not, then you fail to reject. If you are looking at that then, so that's all that says. The p-value approach, we still have to get our z-score, but then we find our probability, which is a little bit easier because we just spent all last unit finding those probabilities. And then to decide if you reject or not, it's actually pretty simple. If your p is less than the alpha given in the problem, you reject. If p is greater than alpha, we would fail to reject. So most of the time we'll look at the p-value, but I wanted to show you the classical as well. And then at the very end, I do want a conclusion. You have to tell me, are you rejecting your null hypothesis, or did you fail to reject your null hypothesis? So you have to tell me what your result means at the end. So let's try a problem. In 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 stated that they did not trust the media. At the alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? So, step 1. You don't necessarily have to label the steps, but you're welcome to. What do we have to have first? What do you think? Hypothesis. We have to know what we're testing before we can even begin doing any kind of test. So, my null hypothesis. We're talking about a proportion. The null is always equal. What was our baseline? What was my original p? 0.46. The alternative. Still with p, what are we trying to test? Increase. So that would be greater than 0.46. So is this left, right, or two-tailed? Right tail. Testing greater than. Okay. Step 2. We have to have an alpha level, which is given in the problem, but just so we make sure we know it, we are looking at alpha equals 0.05. All right, step 3. Doesn't matter which approach we're doing, we still have to do this. We need our z-score. So if we're going to do that, we have to check our criteria, right? Okay, you don't have to show me a ton of work on the criteria, but enough that I know you realize what you're doing. We need to check that n times p times 1 minus p is greater than or equal to 10. What's my n? And my p? 250s, that's good. And is my sample less than 5% of the entire population? Yes. Okay. So your criteria, you're welcome to do those before you do your null and alternative. You just have to do them at some point. All right. So we need, if we're going to get a z, we need the mean and the standard deviation. What is our mean? 0.46. Standard deviation is the square root 0.46, 1 minus 0.46 over my n, which is 1010. You get 0.0157. Any questions so far? So what do we do next? No matter which approach, we need our z-score. So z is our value. Do I even have my value written down? No, so I need that, don't I? So p hat. So z is our value minus the mean divided by the standard deviation. It is important to not round too much on here. If you rounded everything to 1 or 2 decimals, it's going to throw off your answer quite a bit. So try to keep the 4 decimal places 3 to 4 like we typically do. All right, from here, this is where the difference in the two approaches comes in. So you won't have to do both, but I'll talk through them just so you guys can decide what you like. If we're going to have a classical approach, we need to know what z corresponds to our breaking point, our cutoff point. Okay, since it was just one-tailed, that means my whole 5% error can be in that upper tail. So we're looking for a z of 0.05. If it were two-tailed, we'd have to split that 0.05 into 2. So remember, when you are looking at that, that means 5% is to the right. So what's the area to the left? 95. So you look in the table, the closest area you can get to 0.95 is 1.645. So what that means is we found for this approach 1.645 was our threshold. Anything beyond that we would be in our rejection area. We got 3.81. Is that where we would reject? Yes. So since 3.81 is greater than 1.645, we reject the null hypothesis. Okay, this is where it gets a little bit tricky because classical, you really have to think about what kind of test you have. If we were doing the left tail test, less than, then we would reject for anything smaller than that z-value. And if it were two-tailed, we would have first had to split that percent, the alpha level, in 2. we'd have 2 Z values, and if you were bigger or smaller, then you would reject. P-value approach is a little more consistent in that it doesn't matter what kind of test you're doing, you work it the same way every time. We have to find the probability. We are testing greater than, so the probability that Z is greater than 3.81. So you go to your normal table, we look up 3.81, and is it even on our table? No. So the closest we can get is 3.49. Greater than, we do what? 1 minus. So at best, 0.0002, but we know it's really smaller because our table didn't go up that far. And so, since our probability is less than the alpha level, we reject. So in both scenarios, no matter which way you had finished it, you found that we would reject it. So our conclusion, there is enough evidence to conclude the proportion has increased. And I'm saying increased because my alternative hypothesis was that it increased. Questions on that one? Okay. I want to show you how to do this on your calculator as well. So you might want to make yourself some notes. We kind of know from the other tests that we've done in our calculator, if you pick the wrong test, you probably don't have the information to put in. So if it's asking you for stuff you don't have, you probably went to the wrong one. So we would go to stats, tests, and we are going to look at number 5, a 1 proportion Z test. Stats test number 5. It asks us for P sub 0. That's the P for the null hypothesis, which was what? 0.46? Okay, it asks us for our X value. What would that be? That's the 525. Remember, P hat is X over N, so that's 525. My N, my total number, is the 1010. And then you have to tell it which tests are you doing. Not equal, less than, or greater than. And we were doing the greater than. Okay, and then we want to, you can have it draw you a picture if you want, but I just want to calculate. So if we do that, it gives us our Z, which is the same one we got. Why is this probability not the same probability we had? Right, our table ran out of room. Okay, but if normally that will match the probability you found. And so you look at that probability right here, and if it's less than alpha, you reject. So stats test number 5. Do it on the calculator. Questions? Let's do another one. When asked, is it more important to protect the right of Americans to own guns or to control gun ownership? 46% of all Americans said protecting the right to own guns was more important. A research center surveyed 1,267 random Americans with at least a bachelor's degree and found that 559 believed the right to own guns was more important. Does this result suggest the proportion with at least a bachelor's degree feel differently than the general population? Use alpha equals 0.01. So, what do we do first? What's my null hypothesis? And what's the alternative this time? Not equal. I just want to know if it's different. What do we need to check here? Criteria. Okay, my N 1267, P 0.46, 1 minus 0.46 has to be greater than 10. And that one is, and then our sample has to be less than 5% of the total population. Would 1,267 be less than 5% of the American population? So criteria is good. That means we can proceed with turning this into a normal function. So to do that, we have to have the mean and the standard deviation. And we'll also need our p hat in here if it's not given. So the mean is what? Standard deviation, square root 0.46, 1 minus 0.46 over n. We get 0.01400. How do we find the p hat? So 559 and 1267. So 0.4412. All right. So we did step one. We have our hypothesis. We checked our criteria. Do we have alpha? Alpha is 0.1. We are ready now to do what? So z is our value, so the p hat minus the mean, 0.46, divided by the standard deviation. So we get negative 1.34. Okay, from here it depends on if you're doing the classical or the p-value approach. Do you guys have a preference, or do you want me to show both again? P-value? Okay, this is where we do have to be a little bit careful, because my alternative was not equal. Okay, so that means it could be greater, it could be less. So when we find this, we can find the probability that our z, okay, we have to do one of these first. So let's find z is less than negative 1.34. So if I look at that from my table, we get 0.0901. Okay, but if we think about what this means, this is the negative 1.34. But if we're doing not equal, we also have to consider the other end, don't we? What would my z be there? Be it positive, because this is symmetric. So you have two options. you can either find the probability that it's less than negative 1.34 and the probability that it's bigger than positive 1.34. Or you could realize that what should be true about those probabilities? It's symmetric, so those should be the same. So if it is two-tailed, so the only reason I'm doing this is because it's two-tailed. When you find your probability at the end, you need to take it times 2 for both tails. We get 0.1802. All right. Now what do I compare that to? Alpha. Since 0.1802, that is greater than my alpha, isn't it? So what would that tell me? Fail to reject. There is not enough evidence. To conclude, this group feels differently. Questions on that one? Do you want me to talk about how we would have done this with the classical approach? You basically, your alpha level is 0.0 or 0.1 here. So you'd have to divide that by 2, 0.05. Look that up on your table, so you get positive and negative 1.645. So anything bigger than positive 1.65 or smaller than negative 1.65 would make us reject. RZ was negative 1.34, so it wasn't small enough. We would fail to reject. If you do it on your calculator, we should get something pretty similar. So stats test number 5, our P was 0.46, X was 559, N was 1267. This time we tested not equal, so you have to make sure you click that. And then we get our probability. Slightly different because it's just a little more precise than ours. It takes the probability to more decimal places, so then when you multiply by 2, it changes it slightly, but they are very close. All right, questions on that? I am going to stop here for today, so I will finish this section tomorrow. So if you're still working on the 10.1 homework, you need to finish that. On 10.2, you are able to do probably up through question 10.